Hello there, my name is Muhammad Anik Ashraf bin Jahidin. My matrix number is 110911. And in this video, our group would like to do a presentation on our thermodynamics projects, which is the programming of Microsoft Excel on the Rankine cycle. So without further ado, let's get into our presentation. Alright, let's kick off with introduction, starting out with the background of a Rankine cycle. So Rankine cycle is a fundamental thermodynamic cycle used in steam power plants for electricity generation. It is developed by William John McKern Rankine in the mid-19th century. It uses a water or steam or H2O as a working fluid in a closed loop system. A closed loop system means in a circulation closed loop system. It's repeated. And in a Rankine cycle, it consists of four key thermodynamics processes, which is isentropic compression, which is the pump, constant pressure heat addition, which is the boiler, isentropic expansion, which is the turbine, and a constant pressure heat rejection, which is the condenser. As you can see in the diagram, it is in a loop circulation system. So the importance of Rankine cycle is that it forms a theoretical foundation of a modern steam power generation. It is widely used for performance evaluation and design of thermal power system. So the evolution of Rankine cycle. So Rankine cycle expanded beyond conventional fossil fuels in power plants. It applies in organic Rankine cycles or ORC, supercritical and transcritical Rankine cycle, waste heat recovery system, and solar, geothermal, and biomass energy systems. It contributes to improve efficiency and reduce the environmental impact of the world. So for our project context, our project studies focus on the design and the analysis of a Rankine cycle based on the utility plan locally for Yellow Hippo Sindalan Berhad. So it's emphasized on the equipment sizing and selection, energy and mass balance analysis, steam quality management, and the operational safety and efficiency. It is aims to meet specific power demand while ensuring the reliable and sustainable plant operation. The methodology of our projects is that to design and simulate a 15 megawatt Rankine cycle system steam power plant using a Microsoft Excel under a steady state operating system. As for our projects, we define the operating conditions where the boiler pressure and temperature, condenser pressure, turbine inlet conditions, and the target net power output, which is 15 megawatts, obviously. Next is to establish cycle state points, where in state 1 which is the condenser outlet, which is saturated liquid, state 2 pump outlet, state 3 boiler outlet, and state 4 the turbine outlet. As for the state 3 boiler outlet, however, it is a superheated steam, as the Rankine cycle itself. And number 3 is to obtain thermodynamics properties, which is pressure, temperature, specific entropy, and steam quality, X. And lastly is to perform energy balance calculations at the pump work, boiler heat output input, turbine work output, condenser heat rejection, and the net power output itself. And for our projects, we assume that the Rankine cycle that we use is under a steady state operation, ideal isentropic pump and turbine, pure water steam or steam working fluid, and negligible kinetic and potential energy changes. For our thermodynamics property package specification for our projects, the working fluid is obviously steam or water. The properties obtained using steam tables from Learn Chem E, and for our properties used are enthalpy, entropy, temperature, pressure, and steam quality. As for our programming, we use obviously Microsoft Excel simulation procedure. As for the procedure itself, we develop the worksheets for state properties, component energy balance, and performance calculations. As for the calculation itself, however, we calculate the turbine work output, the pump work input, the heat supply and rejected, the thermal efficiency, the steam mass flow rate, and the specific steam consumption. for our expected outputs is that our net power output is around 15 megawatts, less or more, thermal efficiency, steam mass flow rate, turbine exhaust quality, and the component heat and work duties. As for our model validation, energy balance closure check, the comparison with published Rankine cycle performance data with other references, verification of acceptable turbine exit steam quality. And as for our suggested calculation flowcharts, you can see our Excel calculation flowcharts on the screen. It is input operating parameters at first, steam table properties at the second, then move to the energy balance calculations. And for the second last is the performance evaluation, and lastly is the validation of our Excel programming.
Hello everyone, my name is Jodo Bongi with matrix number 108561. A complete process flowsheet of an ideal Rankine cycle was developed in Excel consisting of 4 components: feed water pump, boiler, turbine, and condenser. At the feed water pump, there is isentropic pumping of saturated liquid to compressed liquid. This is followed by boiler, in which the constant pressure heating of compressed liquid to superheated steam occurs. Then, at the turbine, there is isentropic expansion of superheated steam to wet steam, followed by constant pressure and temperature cooling of wet steam to saturated liquid at the condenser. For ideal Rankine cycle calculations, there is interpolation of steam tables for wet steam in order to calculate the thermodynamic parameters. These thermodynamic parameters are calculated by using equations involving the quality of steam. Furthermore, the work done for the turbine and the feed water pump is calculated through the multiplication of mass flow rate with the change in enthalpy. Moreover, the heat transfer for the boiler and condenser is calculated through multiplication of the mass flow rate with the change in enthalpy. Then, the Rankine cycle is modified to be non-ideal. In this stage, the turbine and pipe efficiencies are determined via assumptions. Real enthalpies are calculated from non-ideal work done for turbine and pump via previous equations. Following this, the real thermodynamic parameters are found via interpolation of steam tables. As for the ideal Rankine cycle calculations, the work done for turbine is calculated through multiplication of the isentropic work done for turbine with the efficiency of the turbine. Moreover, the actual work done for the pump is calculated via division of the isentropic work done of the pump with the efficiency of the pump itself.
Hello, my name is Joseph Wong, and this slide summarizes the simulation inputs and validates the results of our 15 megawatt Rankine cycle model. First, the simulation was developed using 4 main operating parameters. The boiler pressure was fixed at 10 megapascals, while the turbine inlet temperature was varied from 325 to 675 degrees Celsius. At the same time, the mass flow rate was adjusted from 19 to 12.2 kilograms per second in order to maintain a constant 15 megawatt power output. After running the simulation, we obtained a boiler heat input of around 50,000 kilojoules per second, a turbine output of approximately 15.26 megawatts, pump work of 190 kilojoules per second, and an overall thermal efficiency of 29.58%. To validate the simulation, the calculated net power output was 15.01 megawatts, which closely matches our design targets of 50 megawatts. The thermal efficiency is also close to 30%, which agrees with values commonly reported for a simple Rankine cycle. However, the turbine exhaust steam quality was only 0.77, indicating excessive moisture that could lead to turbine blade erosion. This issue motivated the cycle improvements presented later. Moving on to selection of key operating parameters. This slide explains why these operating parameters were selected and how they influence the performance of a Rankine cycle. Temperature is one of the most important parameters because increasing the turbine inlet temperature increases the steam enthalpy. With high enthalpy, the turbine is able to extract more energy from each kilogram of steam, resulting in greater turbine work. Since each kilogram of steam produces more work, the required mass flow rate can be reduced while still maintaining the target output of 15 megawatts. Meanwhile, the boiler pressure was kept constant at 10 megapascals to ensure safe and efficient operation, while the condenser pressure remained at 0.004247 megapascals to maximize steam expansion through the turbine. As shown in the engineering relationship, increasing the temperature leads to a higher enthalpy, which increases turbine work. This allows the mass flow rate to decrease while maintaining the same 15 megawatts power output. Therefore, selecting the correct operating parameters improves both efficiency and the overall performance of the cycle.
So next I will discuss the effect of boiler outlet temperature and mass flow rate on the Rankine cycle performance. So in this analysis, the boiler outlet temperature varies from 325 degrees Celsius to 675 degrees Celsius, while maintaining the net power output constant at 50 megawatts. As the temperature increases, the steam entering the turbine has a higher enthalpy, meaning that more energy is available for expansion and power generation. So hence, a lower mass flow rate is needed to achieve the same 50 megawatts output. From our results, the required mass flow rate decreased from 19 kg per second at 325 degrees Celsius to 12.2 kg per second at 675 degrees Celsius. Besides reducing the required steam flow rate, increasing the boiler temperature also improved the thermal efficiency. The efficiency increased from 29.56% to 39.49%. So this shows that operating the Rankine cycle at a higher turbine inlet temperature can improve energy conversion performance and therefore reduce the amount of steam required for the same power output.
As for the tabular and graphical representation of results, Table 3a shows the pressure constant at 10 MPa. This shows the direct relationship between the increasing superheat temperatures and the resulting fluid enthalpy. Following that, for Table 3b, it shows the expanding variable inlet states down to a fixed condenser back pressure of 0.004247 MPa. This shows the actual work output duty while factoring in isentropic efficiency constraints. Next, for Table 3c, it tracks the phase transition of turbine exhaust back into a saturated liquid at a constant saturation temperature of 30 Celsius. This quantifies the total rejected heat duty to excess environmental thermal pollution. Finally, for Table 3d, it models the compression of incompressible liquid back up to 10 MPa. This maps the decreasing parasitic power drain on the system as the overall mass flow rate decreases. As for the Figure 4, it plots the independent boiler outlet temperatures against the dependent system mass flow rates.
So for the simulation, several engineering assumptions were applied to simplify the Rankine cycle analysis while maintaining realistic operating conditions. First of all, the turbine and pump isentropic efficiencies are assumed to be 75%. This accounts for real operating losses such as mechanical friction, fluid resistance, and irreversibility during energy conversion. As for the condenser, the operating pressure was assumed to be 0.004247 MPa, which corresponds to a condensation temperature of approximately 30 degrees Celsius. This assumption represents a realistic cooling condition considering the ambient environment at Samajaya Free Industrial Zone. The cycle was also assumed to operate under steady-state conditions with negligible pressure losses throughout the system. These assumptions are important because they allow the Excel simulation to provide a reasonable prediction of the Rankine cycle performance.
For Rankine cycle analysis, Table 3a shows that pressures of 10 MPa remain constant as heating of compressed liquid to superheated steam occurs at high constant pressure. The initial enthalpy remains constant due to the constant inlet temperature, whereas the final enthalpy increases as the outlet boiler temperature rises from 325 Celsius to 675 Celsius. However, the quantity of heat absorbed by steam in the boiler decreases, even though changes in enthalpy grow wider due to the decrease of mass flow rate as the boiler outlet temperature rises. For Table 3b, the outlet turbine temperatures and pressures are lowered due to the expansion of superheated steam to wet steam. However, these final temperatures and pressures remain constant as they are based on the thermodynamic parameters of steam at the condenser outlet. The final enthalpy increases at a slower rate with the initial enthalpy as the mass flow rate decreases to maintain approximately 15,200 kilowatts of work generated from the turbine. For Table 3c, temperatures and pressures remain constant as cooling from wet steam to saturated liquid occurs at constant temperature and pressure. The final enthalpy at condenser is lower and remains unchanged with varying mass flow rates and boiler outlet temperatures. This is due to saturated water presence and thermodynamic parameters specification based on cooling water temperature. Moreover, the quantity of heat released from steam in the condenser decreases, even though changes in enthalpy increases as the mass flow rate for steam drops. For Table 3d, temperatures and pressures increase as saturated water is compressed to produce compressed liquid. Hence, enthalpy increases slightly but remains unchanged as mass flow rate decreases and boiler outlet temperature increases. The work done for the pump decreases as mass flow rate decreases since changes in enthalpy are constant. This graph shows the relationship between proposed temperatures and mass flow rates utilized for the 15 MW Rankine power generation. As more steam flows within the power generation cycle, required temperatures at the boiler outlet are lower. Hence, less heat is absorbed by the steam in the boiler, reducing energy requirements for the boiler in power generation. As for the overall efficiency calculations, the heat absorbed by steam ranges from 50,000 kilojoules per second to around 45,000 kilojoules per second, for outlet temperatures from 325 Celsius to 675 Celsius. The net power input is constant at 15 megawatts as well. Therefore, the thermal efficiency of the 15 megawatt power generation cycle may be calculated via the following formula. Hence, as the mass flow rate increases, the overall efficiency of the 15 megawatt power generation slightly decreases. Furthermore, as the boiler outlet temperature increases, the overall efficiency of the 15 megawatt power generation increases slightly. Hence, the optimal efficiency is present under the conditions of high boiler outlet temperatures and low mass flow rates. According to the two graphs of thermal efficiencies against mass flow rates and thermal efficiencies against boiler outlet temperatures, the calculated thermal efficiency for the 15 megawatt Rankine cycle ranges from 30% to 34%. This value is within the expected range for a simple Rankine cycle because energy losses occur mainly through condenser heat rejection as well as irreversibility in the turbine and pump. Further improvement can be achieved through cycle modifications such as reheating and regeneration.
Moving on to 3.3, which is cycle modification for 35 megawatts of power generation. Although the baseline Rankine cycle successfully generated 15 megawatts, it could not meet the requirements for 35 megawatts capacity and also suffered from low steam quality. Therefore, two major modifications were made. First up is reheat cycle. Instead of using a single turbine, the turbine is divided into a high pressure turbine and a low pressure turbine. After expanding through the high pressure turbine, the steam is sent back to the boiler for reheating before entering the low pressure turbine. This increases the turbine work, improves thermal efficiency, and most importantly, reduces moisture formation, which minimizes turbine blade erosion. The second modification is regenerative feedwater heating using an open feedwater heater. In this process, a portion of steam is extracted from the turbine to preheat the feedwater before it enters the boiler. Because the feedwater is already warm, less external heat is required, reducing fuel consumption while improving the overall cycle efficiency. As shown in the comparison table below, these modifications increase the power generation from 50 megawatts to 35 megawatts, improve the steam quality from 0.77 to at least 0.88, and transform the simple Rankine cycle into a more efficient reheat and generative cycle. Overall, these two modifications enable the plant to achieve the required 35 megawatt output while operating more efficiently and safely.
Recommendations for project improvements for our researchers is that number one is to optimize reheat and extraction pressure, where it conducts parametric analysis using EAS or Excel-based thermodynamics models, determine the optimum, which is the reheat pressure and steam extraction pressure, and the objective of this recommendation is that it is maximize the net work output, improve thermal efficiency, maintain turbine exhaust steam quality, which is more than 0.88, and the expected benefits for this recommendation is that higher power generation with reduced turbine moisture content. Number two is implement multi-stage regenerative feedwater heating. So replace the single open feedwater heater with multiple feedwater heaters, hence the name. The benefits of this is that it is increased feedwater temperature before boiler entry, it reduced boiler heat requirement, higher cycle efficiency, lower thermal stresses on the boiler components, and improve operational flexibility. So number three of our recommendations for our projects, which is integrate advanced monitoring and control system. What is mean by that? Basically, it's a real-time monitoring of the reheat outlet temperature, feedwater temperature, steam extraction fraction, and turbine exhaust moisture content. So the advantage of real-time monitoring is that it is a stable power output, improved reliability and equipment lifespan, reduced maintenance costs, and better response to varying loads demand of the plant itself. And lastly, number four, perform thermal economic assessment, where it evaluates capital investment costs, fuel saving, maintenance requirements, and return on investment. So the purpose of this is that it is to identify the most cost-effective cycle configuration of the plant, ensure economic feasibility and long-term sustainability, and lastly, justify the implementation of reheating and regeneration upgrades of the plant.
In conclusion, an Excel-based Rankine cycle simulation was successfully developed to evaluate a 15 megawatt power generation system. The results show that increasing the boiler outlet temperature improves the cycle efficiency because more thermal energy is supplied to the steam before turbine expansion. The highest efficiency obtained was 33.49% at a boiler outlet temperature of 675 with a mass flow rate of 12.2 kg per second. Overall, the developed model provides a useful tool to analyze the relationship between operating parameters and power plant performance. For further improvement of this project, advanced cycle modifications such as reheating and regeneration can be implemented to increase power output and improve efficiency. That is all from our group, and thank you very much for your attention.